we were discussing about the intramolecular ene reaction. So when we look like this, we don't get any answer for this. But when we rearrange it like a double bond and an allylic proton, then it is easy for us to have a six-membered transition state. Then we can polarize this hydrogen, then rearrangement of pi bond, then formation of sigma bond. So we can easily expect the product. Okay. You try to write the product. Yeah, what I'm missing is the stereochemical outcome of these ene reactions. I don't know. I did not write this. So you go through any book, okay? Yeah, this is an ene reaction between this allylic hydrogen so that it generates a bond here. 1, 2, 3, 4, 5. So it gives a 5-membered ring. In this case, what we are getting is a cis product. So it is giving more than 95%. When do we expect an ene reaction? An ene reaction can be easily expected whenever we have an allylic proton and an alkene or a double bond. Then we can easily expect an ene reaction. What could be this double bond? So this double bond, it may be an alkene, that means it may be a carbon-carbon double bond, or it may be a carbon-carbon triple bond, or it may be a carbon-oxygen double bond, carbonyl. So it may be any double bond. It may be any double bond. So we don't need to discuss all these examples. Of course, these many questions may not be asked, but yeah, ene reactions are in principle possible with any of these double bonds. Now we will see some more examples on intramolecular ene reactions. This is R citronellal. When it was treated with zinc bromide, it is generating a 6-membered ring. Yeah, this is below the plane. This compound is called isopulizole. What is happening is C double bond hole. This oxygen is picking up this allylic hydrogen. So there is a bond formation between these two carbons. Double bond will be generated. So this is what it is happening. What is the product? when it is treated with hydrogen and nickel. Of course, it is the reduction of double bond. So the product is S-menthol. Product is S-menthol. Similarly, when this compound is treated with methyl aluminum chloride, again it is undergoing cyclization. Again, I am saying the stereochemical outcomes are just copied from the book. Okay. Yeah, there will be a bond formation between these two carbons, and hydrogen will be picked up by this carbon, right? So this is what a ene reaction. This is again an intramolecular ene reaction. So yeah, the stereochemistries were just copied. When these two are treated in presence of a titanium complex, it is undergoing an ene reaction. So the double bond is undergoing reduction, and a bond formation is taking place between this carbon and the carbonyl carbon. So it is an intermolecular ene reaction. Here alkylation, it is nothing but alkylation on the carbonyl. Now we will see a similar alkylation reaction. And it is treated with diethyl aluminum chloride or tin tetrachloride. It is undergoing alkylation on this carbonyl. So there will be a bond formation between this carbon and this carbon. So it leads to a 6-membered ring. Then proton from here will be shifted to carbonyl oxygen. So what is the product here? Here it is forming an alcohol, and this is the double bond. What are Woodward-Hoffmann rules for cycloaddition reactions? Woodward-Hoffmann rules tells you that what is the preferred bond formation or preferred orbital orientations that leads to bond formations in cycloadditions. So we will take it as a small table. First one, total number of pi bonds. total number of pi bonds in the reacting system. This is one heading, total number of pi bonds in the reacting system. Then reaction conditions, whether it is a thermal condition or a photochemical condition. Then allowed mode of ring closure. Then allowed mode of ring closure. Now, if the total number of electrons if the total number of pi bonds are even number, like 2 plus 2. So what is 2 plus 2? It is a reaction between two pi bonds. So it is an even number. Right. 2 plus 2 reaction under thermal conditions, it will follow antarafacial. Right? Even number under photochemical conditions. So that means when we pass light, it follows suprafacial bond formation. When we have a total number of double bonds as the odd number, so when we have odd number of double bonds, that means it is a 4 pi plus 2 pi. So 2 double bonds plus 1 double bond, 3 double bonds. Under thermal conditions, it is a suprafacial bond formation. Under photochemical conditions, it is reverse. It is antarafacial bond formation. Right. Sorry. Right. So you see here, if it is an even number of double bonds, then under thermal condition it is antarafacial. If it is odd number of double bonds, thermal condition it is a suprafacial. So odd number means Diels-Alder reaction. So under thermal condition it is a suprafacial. Of course we have read all these things, but we don't know in terms of a rule. So the same system, that means 4 pi plus 2 pi, under photochemical conditions, when we pass light, it undergoes antarafacial bond formation. Yeah, in the even number of double bonds, under thermal conditions, it is antarafacial. Photochemical conditions, again, it is reverse. It undergoes suprafacial. Because of antarafacial is not possible in 2 plus 2, so it is not happening. But 2 plus 2 in 2 plus 2 in photochemical conditions is possible because it is a suprafacial interaction. It is not a antarafacial interaction. So 2 plus 2 reactions are possible under photochemical conditions. So we will look at all these points when we discuss photochemistry.